In fluid mechanics and heat transfer, the ratio of dynamic viscosity, which is this, as we said, viscosity got at least four names: viscosity, dynamic viscosity, absolute viscosity, coefficient of viscosity. So if you take viscosity and you divide it by the density, which is this, then we call this ratio the name kinematic viscosity, and it is given the symbol nu. So my question to you again, I want you to go and look what is the meaning of the word kinematic. So take a note and go and search for it and know it. Maybe I will ask you about it one day. So for convenience, this ratio, which is viscosity divided by density, is called kinematic viscosity. Now let me ask you another question. What is the unit of the kinematic viscosity? So you can think about it. You know what is the unit of viscosity, you know what's the unit of density, and you can try the unit of the kinematic viscosity. You know how to do this. Okay, so this is kinematic viscosity, this is viscosity, this is density, and you can just put the units of viscosity, the units of density, and get the units of kinematic viscosity. I will keep this for you to do. Now, this is the answer, but you know how to do it by yourself. So in fluid mechanics and heat transfer, yeah, this is just a repetition. And then this is the equation of kinematic viscosity. And here is the answer. Two common units of kinematic viscosity are meters squared per second and stock. And one stock is equal to 1 centimeter per second, which is equal to 0.0001 meters squared per second. So stock, as you can see, it is equal to this, and you know that it is in the CGS system, centimeter gram second system. As I said in the previous slide, you can practice it. It is a clear slide. You can practice it to get that. Okay, the Stoke, which is the unit of kinematic viscosity, was named after Sir George Stokes, and he was, he was a mathematician, physicist, politician, and theologist, and he made George Stokes, he made important contributions to fluid dynamics, including the Navier-Stokes equations, optics, mathematical physics, and this is the scientist upon which the kinematic viscosity was named, after which it was named. Now, from now on in this, let us say in this online lecture, we want to know what is the effect of temperature on viscosity and kinematic viscosity of liquids. So from now on, we want to study what's the effect of temperature and pressure on the viscosity and kinematic viscosity on liquids and gases. This is the main topic. Now, suppose I ask you this: what is the effect of temperature on the viscosity and kinematic viscosity of liquids? If I increase the temperature, what do you think will happen to the viscosity of liquid? Is it going to increase or decrease? You can think of honey. You can think of honey in the summer, for example. What's happening to it? What's happening to its viscosity? In the summer, it is hotter. So usually we notice that honey will become less viscous. So we can conclude then for liquids, if temperature increases, then the viscosity will decrease. But what about kinematic viscosity? Maybe we cannot just observe it easily. So we have to go back to the equation. Kinematic viscosity is equal to viscosity divided by density. So if temperature increases, we know that viscosity will decrease. And if temperature increases, so let us look at density. Density is equal to mass over volume. So if temperature increases, mass will not change. What about the volume of the liquid if temperature increases? So it might expand a little bit. So if this increases, so density will decrease, isn't it? Because this ratio will be less. So this is more, this is constant, so density will decrease. So this will decrease and this will decrease. So what's happening here? I mean, this is an effect that contradicts each other, because increasing the viscosity, decreasing the viscosity will decrease the kinematic viscosity, but decreasing the density will increase it. So there is a counter effect here. But maybe one of them will, let us say, the effect of it is more pronounced. It's bigger than the other one. Okay, so I'm just raising this question, but this is how you do it. I mean, if you are asked, what's the effect of temperature on the kinematic viscosity, then you have to look at what's the effect of viscosity, what's the effect of density. At least you can analyze it. After a little bit, I will give you the answer for this. But I want you to know how to think about it. Another question is, what is the effect of temperature on viscosity and kinematic viscosity of gases? The previous slide, we asked the question, what's the effect of temperature on viscosity and kinematic viscosity of liquids? Now I'm asking, what is the effect of temperature on viscosity and kinematic viscosity of gases? I don't know if you have a clear answer in your mind, but let's go on. Another question to be asked here, what's the effect of pressure on the viscosity and kinematic viscosity of liquids? Again, I'm asking this question. So now I'm studying the effect of a pressure. What will happen if I increase the pressure? What will happen to the viscosity and kinematic viscosity of liquids? Next slide. Again, what is the effect of a pressure on viscosity and kinematic viscosity of gases? So I asked all of those questions. What's the effect of temperature? What's the effect of pressure for the viscosity and kinematic viscosity for gases and liquids? Now, those are the answers, but you know how to analyze them. So for liquids, both the dynamic and kinematic viscosities are practically independent of pressure. So for liquids, pressure doesn't affect dynamic and kinematic viscosity, and any small variation with the pressure is usually disregarded. Disregard means it is negligible, it is neglected, except at extremely high pressure. The viscosity of liquids decreases with temperature. And this is from our, let us say, daily observation. If temperature increases, then viscosity will decrease. And this is for liquids. Now, for gases, the dynamic viscosity is independent of pressure. So again, now the viscosity for gases is independent of pressure at low to moderate pressures. However, the viscosity of gases increases with temperature. This is different than for liquids. We said for liquid, as temperature increases, viscosity decreases. For gases, as temperature increases, viscosity increases. And then also the kinematic viscosity is affected by the pressure, since the density of a gas is proportional to its pressure. Okay, let's look at this, let us say, figure here. So at 20 degrees centigrade and 1 atmosphere, the viscosity of air is this 1.83 times 10 to the minus 5 kilogram per meter second, and the kinematic viscosity is that. At the same temperature now, at 20 degrees centigrade, but now we raise the pressure 4 times, okay, 4-fold. It was 1 atmosphere, now it is 4 atmosphere. what happened? The viscosity didn't change. It is 1.83 here, it is 1.83 here. However, the kinematic viscosity did change. What happened to it? It dropped. It dropped from 1.752 times 10 to the minus 5 to 0.38 times 10 to the minus 5. Okay? How to analyze this? Again, you can just go and look at the equation of kinematic viscosity. Nu is equal to mu over rho. And then look at what's happening to the density. You can analyze this yourself. Okay, you can analyze this yourself. So again, for the gases, the dynamic viscosity is independent of the pressure. The viscosity of gases increases with temperature. The kinematic viscosity is affected by the pressure, since the density of a gas is proportional to its pressure. So as can be seen from this figure. So this is mathematically. What I have just explained is mathematically. You look at the equation, and then you said, yeah, I can see it from the equation. This slide now is asking you, the viscosity of liquids decreases with increasing temperature, while that of gases increasing with the increasing temperature. Why? Now I'm asking about physically, what's happening on molecular scale? What's happening to the molecules? Why we're getting such, let us say, such a result on a molecular scale? This is the answer here. Let us read it together. So viscosity is caused by the cohesive forces between the molecules in the liquids and by the molecular collisions in gases, and it varies greatly with temperature. Now, also it is said that in a liquid, the molecules possesses more energy at higher temperatures, and they can oppose the large cohesive intermolecular forces more strongly. As a result, the energized liquid molecules can move more freely. So in the liquid phase, they are already close to each other. If I increase the temperature, they will get, let us say, apart from each other. And now in the liquid phase, as we can said, or as we just said, viscosity is caused by the cohesive forces. Viscosity is how the molecules attach to each other. If I increase the temperature now, they are getting further away, so the cohesive force getting less, so viscosity is getting less. And this is for the liquid phase. On the other hand, in the gas, the intermolecular forces are negligible. They are already weak, the forces between the molecules. And the gas molecules at high temperatures move randomly at higher velocities. So they are already, let us say, they are already apart from each other. They are away from each other. If we increase the temperature more, then there will be more chances for molecular collisions. Now the molecules can collide with each other, and which means with this collision they might come closer and the viscosity increases. This is a table here, as you can see, table 2-3 in your book, which lists some dynamic viscosities of some fluids at 1 atmosphere and 20 degrees unless otherwise stated. So we look at glycerine here, and as we increase the temperature, as you can see, the viscosity dropped. As we increase the temperature, viscosity decreases. For engine oil, we have different types of engine oils, as you can see, and the viscosity is just different for different types. The viscosity of mercury is 0.0015, and this is kilogram per meter second, which is same as what? This is same as maybe Pascal, as we said, Pascal second. So what is the viscosity of mercury compared to the viscosity of water? I will keep this for you also to think about. Water, as you can see, as I increase the temperature, the viscosity decreases from here going on. And then we have the, what else? Blood, gasoline, ammonia, air, and so on. So this is a summary of different viscosities of different fluids.